Let's see how that works. Hi, everybody. I'm Thomas Graf, and I brought a colleague from me, Marco Tollini, with me. So today, I'd like to show you a little bit what we are doing at Swisscom with network analytics. Let's start with our problem space. So nowadays, everybody has smartphones, right? Use internet at home, at business. So therefore, if something on the Swisscom network is changing, regardless if it's operational, a link goes down, a router goes down, line card is failing, or if there is a configurational change, can be either automated or also manually from a network engineer. It's hard to actually recognize the service impact before the customer sees it. So having so many different forwarding paths in the network, so many different configuration lines, it's really hard to detect them. But actually, it's not really an operator's problem, it's an industry problem. So I'm also at the IETF, basically where the network telemetry protocols are being standardized. And one of the problems we see there is basically just about 10% of the work is actually going into network automation and network monitoring. And if you look closely, out of this 10%, only about 2 or 3% is really going into network monitoring. Most of it goes towards network automation, like netconf, yang, and so on. So nowadays we still use in our networks monitoring protocols like screen scraping in CLI or SNMP, things which were designed like 40 years ago. And if you look at IETF and you search about protocols which have built-in debugging capabilities in, you just come across very few. And two are notably IPFIX, so basically when you forward traffic through a router, it basically debugs the forwarding, mirrors the data plane, adds some dimensions, and the same way actually also BGP Monitoring Protocol is doing the same way for BGP. So basically if you get a BGP update message through a peer, you mirror that, add peering dimensions, maybe RIP dimensions, and even route policy dimensions, so you understand through which policies basically this update went through and how it's being installed. So if we would have more than those two protocols, basically visibility in the network would be much more easier. These are two newspaper articles, you know, when something is failing and not working, everybody knows it. So I like these two articles because I can tell a good story. So if you look at the dates, so the left one is February 2020, and the right one is 4 months later in June 2020. The difference between the two newspaper articles is basically network analytics. So on the left-hand side, we had visibility into our network, but we were changing in the core network something, which I will describe in the next slide. And the visibility was on the provider edge. And unfortunately, when you change something in the core and you have the visibility outside of the core, you're not fast enough. Therefore, the outage was longer than we wanted to be. And on the second time, when we also had visibility in the core, we were able to see basically the change in the core much more quicker. And let me explain you a story there. So the change in the core, what we did, is basically a life cycle. MPLS doesn't scale unlimited anymore, so there is a limit of 1 million labels. So that's why service providers are moving now slowly towards segment routing. So first MPLS SR, which is still keeping the MPLS data plane, and in the next step going to SRv6. Now, on that morning, on the 28th of June, basically difference to the February was that in February just a handful of network engineers were actually performing the change in the network. So 4 months later, you can anticipate that there was a lot of attention on that migration. So not only network engineers were present, also management was present, also people who are responsible for application was present, and even newspaper reporters were present. So there's a lot of pressure. So just imagine for one moment you are the network engineer sitting in front of that keyboard and you hit enter and then anxiously waiting and see if the change is actually working or not. So what happened then basically is that within 3 or 4 minutes, we gathered millions of data points from the network. And we saw at the end, this is just one of the graphs, we saw basically where the drops were happening in the network and for which basically MPLS labels we were dropping on which device, on which interfaces, for which path. So what happened is we hit enter. We were anxiously waiting for getting the data. And about 3-4 minutes later, we saw, yeah, the network converged. There were some drops, but now everything is fine. And we understood why it dropped. Now, we were relaxing, said, okay, migration is over, we did our job. The next thing which came in is like our colleagues who are responsible for the application were asking, did you change anything in the network? We didn't see anything. And the next thing is like management was confused, and the reporters were confused because they had nothing to report to. So this is basically, I want to tell with this story the difference. If we have the visibility, if we are seeing what we are changing in the network, it's all super relaxed. When we don't have the visibility, then the stress is basically starting because we don't really know how we are changing the network. And that's where basically the trouble starts. So what I'm showing here is actually, I think, especially at the lower part, every network engineer here knows by heart. So this is just the way how we are collecting the data from the network. This is like the model which is defined in the network telemetry framework. So you have like a device topology, which is like the physical network with the configuration. You have a control plane which is steering the network, and you have a forwarding plane where you actually forward the packets throughout the network, and also the router tells you what he's doing with those packets, if it's being forwarded, consumed, or being dropped. And they all have a relation to each other, and when we are able to actually export the data one-to-one, how it is on the network, make it available in a database, and then basically able to query, you get basically the same visibility as you would have on a CLI, but now centralized into one database, and you can actually much more faster query the network by looking at multiple angles. At the top, to make it easy accessible, you have a service model. So for instance, if you have VPNs like layer 3 or layer 2 VPNs, it's all about a VPN identifier and endpoints, and we need to make sure that the configuration, for instance, the VRF or the interface, or also the BGP communities, if you do MPLS VPNs, are basically matching to that service model. And then through that, you can actually, from top down, verify the network. In order to actually get all the data from the network, you have much more than before, like when you were just doing SNMP polling. So basically the challenge will be how you can actually collect vast amount of data from the network, and pretty much we know it from decades, how to distribute traffic across the network. It's basically ECMP, anycast, and by adding BFT, we can add also basically redundancy, or in other words, it's a giant load balancer. And that load balancer is actually not only going to different collectors on different sites, but then in the next step also within a server, we are balancing thanks to the SREUs port in the Linux kernel and some enhancements we did with eBPF. We are balancing the traffic, the network telemetry traffic towards the data collector daemons. And since we have different collection protocols, so IPFIX for the forwarding plane, BMP for BGP control plane, and YANG push for the device topology, in order to correlate the data as early as possible and aggregate, compress the data as early as possible, we need to make sure that basically one router ends up basically on the same daemon. Therefore, the entire load balancing on the network, but also on the server itself, we need to make sure that they're being hashed in a like two-tuple hash. So source destination IP address. So at the end, just as this brief example with Facebook, the whole query is getting very simple. So Facebook has a dedicated AS number, so we can see basically the traffic on the right side going or coming from Facebook, and on the left side down basically the advertisements of the prefixes of Facebook and how they are correlating to each other. That will be my part now. I'm handing over to Marco. He will show you a bit more what you can do with that kind of data.
So thank you, Thomas, and hi everybody. My name is Marco Tollini. I joined Swisscom about 1 year ago, and just to steal a bit from the first presentation, I'm Italian and I know English not because I studied in US, but because I live in a country and I don't know German. So I need to live somehow. So I'm going to present a bit about our new project. It's called Cosmos, and first I need to introduce you a bit of how we use community and our community concept. So basically, every customer has a VPN and layer 3 MPLS VPN. And to each endpoint, we assign a community. And here you see it as 64499. That is our prefix for the endpoint. And then we have, of course, a route distinguisher. The route distinguisher, as we know, is used so that every prefix between VPNs is unique. And finally, we have a community for the VPN itself, and that is what you see in the middle. It is 64997 is the prefix for that VPN, and then, of course, there is a unique number. So once we have this information, thanks to our wonderful collector, we can merge information coming from BMP or BGP, and then we can augment IPFIX information with the community so that we know where that flows is coming from. So at the moment, as Thomas showed, we have this left view. This is a table view of events in each node. But we have thousands of nodes. We have a lot of events, hundreds of thousands of events. So, sometimes network engineers are a bit lost. So what we are working on, and this is the Cosmos project, is what you see on the right. So we want to visualize a layer 3 topology. And we want to show the state of the network and not the events. So let's see how we are achieving that. We start from these 3 protocols. So we have IPFIX, YANG push, and BMP. BMP stands for BGP Monitoring Protocol. And well, at the moment, Cosmos uses only BMP, but we want to implement also IPFIX and YANG very soon. And from these 3 protocols, we want to go to this network visualization. And of course, there are challenges, as every project, I guess. Here you can see basically a timeline with 4 T's, where T is the time. And at T1, we advertise prefix 1. At T2, we advertise prefix 2. And at T3, we withdraw the first prefix. And now at T4, we ask, what can seem as a simple question, and that is, what is the current routing table state? Well, in this case, it's obvious. It's 2.2.2.2, easy. And now you have to consider that, unfortunately, there are limits in our architecture. We don't have a limited amount of space. And so now we introduce the concept of retention time. So basically, we can, in this example, we keep 5 T's of retention time. So everything that happened before T3, we have to delete. And so now you see that events doesn't really work for the state because, we lost T1 and T2 information, which are the two advertisements. So now when we try to calculate the routing table state at T8, we say it's empty, but actually we lost .2.2. And now let's say that we have a server farm and we put 100 petabytes of data of hard disk or whatever, so we have all the space in the world. Still doesn't work because basically we see that to really calculate the state of each router, you need to start taking the events from when it boot up at first, maybe 4 or 5 months ago, and then join all the data together. And that might be, I don't know, 20, 50, 100 gigabytes per router, times thousands of routers, doesn't really scale. So basically, the whole problem is simply solved by introducing a dump, or more regular dumping of the routing table. And by the way, this dump does not come from the router itself, so we don't put any strain on the router. This comes from the collector. As we said, the collector has BMP or BGP information already so that it can augment IPFIX. And so he already has basically the whole routing table of each router, which we just dump in a database. So basically now we dump at T4. And so at T4, we basically have a snapshot of our network. And now when we want to calculate the new routing table state at T8, it's just a matter of finding the closest dump, T4, and then we add all the events after between T4 and T8. And now we have the correct state. And of course, this is also cool because, if you have not much space, you do infrequent dump, and of course, it's going to be more computationally expensive. If you have a lot of disk and not much computational power, you can just put more frequent dumps. So you basically can play around with that. And in our pipeline, we have the network device at the very left. Then we have PMA CCT, which we already heard today. Fantastic collector. It does the correlation. This is the piece of code. Then we ingest the information into Kafka, which is our message broker. And from Kafka, with a connector, we go to a timescale DB, which is basically Postgres with time series support. Can be really any database, to be honest. So let's see it in action. You basically have this web interface. You first select the time where you want to see the state of your network. So we select a time, then we select a VPN, and we usually care about one client at a time. So we basically need to select just one VPN. Support for multiple VPN might come later. And then we have multiple visualization, and this is basically the cool part I would like to talk today. We have 4 right now. The first one is called VPN topology, and this is the simplest one. We basically just put all the PEs and CEs of a VPN and their respective RDs into a map, and in the middle, the green point is basically the VPN identifier. So if you click on a node, you can see all these RDs that are participating in the VPN from that node, and so on. And so how do you achieve that, right? From BMP, which is fantastic tool and fantastic protocol, you have basically all the information you need already in your table. You just have to get, first, of course, you need to select the VPN you care about. So basically, we remove the second line. And then we have the loopback, the RD, and the RD origin. And RD origin basically means if it comes from the BMP per P header, so basically if it's the router that is sending the RD from the header, or if it comes from BGP, and BGP means that the address is basically VPN v4 addressing, so with the RD inside. And we don't really care about our P part, so the P core, so we basically remove all the BGP. We just keep the BMP part. So we have 3 lines, and from here, it's pretty trivial. You can draw the map. So of course, this is the simple example. You can, for example, immediately see if a P got disconnected for some reason from your VPN. The second one, it's more interesting. Here we add routing information to our topology. So again, how do you do that? Here we have to add a couple of columns. First, next stop, which of course we all know what it is, and then the type, and this is actually basically the RIB. So if it's out, it means that we are going to share, we shared this information with some neighbors. If it's local, it's in the local RIB. And so we basically need to generate from these two subtables, one where we say that the next stop is self, so we are sending out information, and indeed the type needs to be out. So we know that we are sending some information of which we have some routing knowledge. And this is one of the two tables. The second one is basically where we want to know when the next stop is not ourself. So loopback and next stop must be different, and the type must be local, so that we know that we install the route locally in our RIB. And then you can join the two tables on the same next stop, but different loopbacks, and now you basically have the routing of your VPN. And of course, in this image, I also show the P router. Obviously, this is routing, so we don't draw the P core part, nor the P ring. And well, if you do the math, this is basically what it works, because the first line we have next stop self without, and the second line we import that path, and so there is a line between 1 and 2. Then the third view is peering topology. So here we put peer into context, and this is a bit more tricky. Unfortunately, we have this local IP and peer IP that we need to use, but this information is just when you do the peer up. But in the peer up, we don't have VPN information. So basically, first we need to have route monitoring messages, which is basically when you use withdrawal or updates. And you need to get the list of Ps and Cs and relative RDs from that are participating in a VPN. Once you have that list, then you can use that list to filter the peer up information, so that you have local IP and peer IP. And then finally, you have to join twice the resulting table, so that the local IP of, let's say, the first table is equal to the peer IP of the second table, and vice versa. And now you will have that, you have the peering information. So in this case, first line is loopback 1, is local peer 1, peer IP 2. Second information is local IP 2 and peer IP 1, and so there is a line between 1 and 2. And so from this you have the peering information, and finally you can really see the adjacency of each router at any point in time. So that's it for Cosmos. Back to Thomas.
Thanks, Marco. So as I said in the beginning, I think in a service provider network, it's quite challenging because of all this redundant and this many millions of paths, route policies, VRFs, and so on. So to keep the overview, to make sure that everything is redundant from any endpoint to any endpoint, it's quite a difficult task. And also that if you do a failover from one router to another router, that you actually know before you actually failovering basically which forwarding path is being used for all the given paths you have in the network. So we need really like the visibility within BGP, and until now, basically by just peering to the router, getting some BGP routes from the router, we do not have really the real visibility of inside of the BGP router. So a BGP router has basically an adjacency RIP in, where we learn a local RIP, what you install, an adjacency RIP out, where you advertise, and BMP, the initial basically RFC was covering the adjacency RIP in part, so what we receive. In the meanwhile, adjacency RIP out is also being an RFC since about, I would say, 2 years. And the local RIP, basically covering the local RIP part, is now at the RFC editor and soon will be an RFC as well. So now, having all the visibility in all the RIPs brings us a new challenge. We don't know anymore in the local RIP which of the routes are actually how installed into the RIP, because some of the routes in the local RIP are not even considered to be installed, others are considered to be installed, some of them are either active, some are passive, some of them will be ECMP, or in other words, BMP already has a so-called per peer header, so we understand on which peer we are learning those routes or advertising the routes. And now with these drafts, basically, we are also getting the RIP dimensions, so we know how the routes are being installed. But that's not the end of the road. The last thing is about route policies. So at the end, we want to understand why a route is not being installed in the local RIP. So we need to understand through which route policy, at which attachment point, basically the prefix passed, and also if the prefix has been passed through the route policy or not, and if it's passed, if there were any changes, and if yes, what changes were performed on which attributes on those prefixes. So this is basically how we can get the full entire view within a BGP router. For IPFIX, you saw in the beginning, for us segment routing is important. So IPFIX gives us the coverage of the forwarding plane. These are the two drafts basically covering all the segment routing specific attributes needed to actually see also the segment, the labels, and also to which loopbacks basically the forwarding is happening in the segment routing. Here, it's another thing which we are working on is so through netconf Yang. So netconf is basically the API where you're configuring a router. Yang, or the so-called Yang data store, is basically where the configurational and operational metrics are being stored on a router, and Yang is the schema describing that information. So I give you a simple thing. For instance, if you think about an interface, so you have a Yang model for interface, and in this Yang model you have one part saying, I want to shut down an interface, and on another part on the same tree you actually see that the interface is on shutdown. So that helps to bring basically the two worlds, configuration and operational, together. And at the end, what we want to achieve is that the Yang data store you have on the router, you have an exact copy of that Yang data store outside of the router. So at the end, it's basically just a syncing process. So when you're pushing a new configuration out, you're getting operational matrix back and insert that into the same database. And then you can actually do what if. So you can simulate in that Yang data store changes in the network without actually applying any configuration in the network. But for that, we need to bring the two worlds, network and big data, together. Unfortunately, they don't speak the same language yet. So now our next task is actually to bring Yang as a schema definition language into big data, and also the serialization, JSON and CBOR into the message broker. Here, just in a nutshell, the difference between BMP, IPFIX and Yang push. If you want to know more what's going on at IETF, you can go on this link here. Also, if you're in a university and looking for a master thesis, that could be something interesting to actually enhance the data collection to support high availability for BGP Monitoring Protocol. And last but not least, a master thesis which we just finished with ETH is about to bring this load balancing, which I just described before, with eBPF into the SREUs port into the Linux network kernel. That's all. Thank you very much. Any questions?
I've got one. It might be slightly out of context. With all the data you're collecting, what sort of timescale are you working on? I mean, we're talking milliseconds, microseconds, nanoseconds, and how do you align it on the same timeline in order to correlate the data?
That's a very good question. So Basically, for the forwarding plane, we are using flow aggregation. And as the word implies, it's aggregation. So the aggregation happening on the line card on the router, but also on the data collection. And we are currently aggregating to the minute. And also when we are indexing in the time series, it's to the minute. Everything else is basically just, so the BMP part is like live, like the changes from the network. We index them also in the minute. And the young push part, there are two kinds of subscription. On change, when you change on the network, periodically it's also every 60 seconds. So it's basically per minute.
Okay, so your granularity for events is on a minute scale.
Exactly.
Do you see value in drilling to something that will be at a smaller scale? I mean,
let's say we see it basically when we were stress testing BMP in the lab, that basically when you need to measure like the additional overhead you have with BMP, which is very slightly, if you want to measure the propagation delay, then basically you need to really go down like in the seconds or microseconds to see the difference.
Okay, thanks.
I spotted that you were using only extended community. I was wondering if you considered large BGP communities.
There are 3 different classes. Standard communities, so you know that there are just 16-bit. So we also support large communities, and extended communities are currently used for MPLS VPNs like route targets or site of origin. Yeah.
I have a question related to timescale DB.
Sure.
Please.
Do you use compressed hypertables on certain data?
Not yet. We are working on that. I mean, at the moment we are just in lab, so we don't really need to compress much data. We are still testing around. Ideally though, timescale probably will not go ever in prod for us, or we don't know yet, let's say. Because it doesn't scale enough. As you can imagine, we have thousands of routers, millions of metrics per second. So timescale is a bit on the limit. But on the open source part, will be without probably compression, and then a user can enable it if he wants to.
Any more questions? Okay, then, yeah, thank you very much.
Thanks as well.